going to talk a little bit about what research I did so that I knew what elements were most important in this drivetrain. To test the grip of different wheels, I built this little guy here. It may not look like much, but it's actually a very small car with a single motor, just designed to test the grip of different wheels. Mecanum wheels actually have the lowest grip, it seems like. Omni wheels are already better, but these kind of rubbery, soft wheels, they have way more grip. That's of course the main benefit of a swerve drive, but it takes quite a long while to design, so I haven't done that right now. Also, for some more research on grip, we actually talked to some experts over at VertiDrive in Rotterdam. We went there with part of the team, and they had done a lot of tests with grip on different wheels. They use it on the surface of ships, so it's a slightly different environment, but it was still really interesting, and we learned a lot, and we of course had a great time. Now I'm going to tell you about how I really designed this drivetrain to arrive at this final product. During testing, I actually built an entire test Mecanum drivetrain. On the outside, it probably looked very similar to this one here, but actually there are some differences. The main one being that in our first test drivetrain, the battery was actually mounted all the way at the back. It was kind of mounted right here, under where the controller is now. And since the battery is a very heavy part of the drivetrain, the center of gravity was really all the way at the back. And that meant that the rear wheels had slightly more grip, and it actually changed the way the robot moved, in the sense that while strafing, the two rear wheels turn opposite each other, and if they have the most grip, then that will actually turn the robot while strafing. By putting the battery all the way in the middle of the robot, this actually helped a huge amount, because now the heaviest parts of the drivetrain, which include the motors and of course the battery, which I just talked about, are all located in the middle, which means we are very maneuverable and don't have this this stupid effect, which means that the robot doesn't behave like it should, basically. In the testing phase, we also noticed that having a little bit of slack on the timing belts really increases the load on your motor, as the amps going through the motor increase a lot if there is some slack. This couldn't really be solved in my first design, so in this final product there are these holes in the side plates, which we put a screw through, and a kind of roller that will actually push the timing belt down, which increases the length, and by choosing one of these holes, actually the tension of the belt can be adjusted really easily. One thing you might notice straight away when looking at the design is there are these big holes or cutouts everywhere. For instance, here and here, next to the control hub. You might not immediately recognize their function, but they are actually primarily designed to make cable management a lot easier. For the last 2 years, we've really been making a big mess when it comes to cable management, where these cables just everywhere, basically. But this makes it way easier because the cables can just go through the pieces instead of around them. In our last robot especially, there were cables at places where they really had no right to be, because they had to go around everything and had to do a certain length, and this really makes that a lot easier because the cables and the wires can just go through everything, basically. It's still a bit of a mess right now as it's a test version, but we hope to improve that in the future. Something else which you might notice right away is there are a lot of wooden pieces. They are all angled slightly differently, so the side plates are of course parallel, but there are kind of top and bottom plates, like you can see here, this part. And actually this plate at the front is actually slightly diagonal. This greatly increases the stiffness of the overall design. If you can see, I can really only lift one wheel up by maybe a centimeter before the other wheels start to go up as well. So that's really that's a great improvement compared to our last design, which was basically flat. So there could be a lot of motion between different parts of the drivetrain. And this would make definitely software a lot more complex. This was a short overview of the new drivetrain which I designed. If some problems occur, I might consider making a second version. I've already got some ideas to, for instance, improve the overall stiffness of the design. However, I've also got a very exciting new project that I'm working on. So when that's finished, you will hear from us again. Thank you.